Assalamu alaikum warahmatullah. Hello guys, today we will talk about chapter 6, deep feedforward networks. So in this session we will talk about multi-layer perceptron, or this first network in deep learning, and we will solve the problem of exclusive OR, and we will talk about architecture design, about hidden units, and about output units. Let's get started. So deep feedforward networks, neural networks, okay? Why we call them feedforward? Because the information basically flows from input X to the model, to the internal computation, and in the end, finally, it results into the Y output. So because of this flow of information of this X input going through each layer in the network, we call them feedforward. And why we call them networks? We call them networks because we can represent them as chain of function, so that X input goes to the first function, and then this first function goes as input to the function 2, and then function 2 goes as input to function 3. So here we can see there are 3 layers or 3 functions, and as you see, information X goes to to function 1, and then function 2, and then function 3, and it gives us the result of the model. So because of this connection, because of this chain of connection, we call them networks. And we can say about these networks that F1, we can call them as layer. F1 is layer 1, F2 is layer 2, F3 is layer 3. And F1, we call it input layer. F3, because it is the last function, we call it output layer. And everything between, we call them hidden layer, or second layer, third layer, or we can call them inner layer, or whatever you want. And so if we talk about depth of the model, how deep our model is, we refer to the number of functions inside this input, between the input layer and output layer. And we call the width of the model for if the dimension of the vector inside these layers is big. And okay, we covered about feedforward. What is feedforward? We studied what is deep means, and we studied about network, and let's talk about neural. So neural networks, we call them neural networks. Why we call them neural networks? Because actually artificial intelligence and this kind of multi-layer perceptron is inspired from neural science, and it resembles how our brain works actually, because assume this one layer is a bunch of weights, matrix weight, and the input comes as another vector or as a matrix, and here it will become the computation. So each value goes to each unit, and it results in another value, and another value goes to another matrix or another vector. So we can represent this kind of calculation as units. Each row is unit, so that one unit gets input from many different units, and it gives the output to another unit. So because of this resemblance of how our brain neuron works, we call them neural networks. Basically, that's all. And I want to tell you about one important thing, and that it might be very clear for you, inshallah. So we saw the problem that our linear models are good enough, right? If we draw our data set, if we can draw line, then we can implement the linear regression or other linear model, and it will perform good. But we say that these linear models are limited, right? The capacity of the model is limited, and if we give some kind of a non-linear distributed data set, it cannot learn. So what we can do in that case? So in that case, scientists gave us three options. So first option, let's transform this input x into the specific dimension where we can draw a line. Okay, and this transformation to specific dimension, we can transform them by using the RBF kernels, or we call them as Gaussian kernels, and they are similar to how support vector machines kernels work. And so we can change this input x to another dimension where we can draw the line. So that's solution, and it works, it's good. But the problem with this solution is that even though we draw successfully the training set, we transform the training set and we train the model often remains poor on the validation and the test dataset. So which means not very good thing, because these RBF kernels are complex, and the capacity of the model, it will increase the capacity of model, and it will also introduce some extra generic things. In that case, scientists said, let's use second approach. In second approach, let's manually, by our human power, create that transformation. So maybe the transformation of some kind of function, we will create some kind of function to transform the input x to another dimension where we can draw clearly the line. And that kind of transformation, that manually engineering this transformation, was actively searched before deep learning was there in literature. And second approach is good, but actually it is excellent way, but it is limited because it costs a lot. It is expensive because engineering manually for each problem, for each AI task, it is expensive, and it may even take 100 years, or it will take so many years. And in that case, we said, okay, let's then introduce the strategy of deep learning. So let's give the deep learning to define this phi function, transformation function, and we will give these weights and biases to this deep learning. So deep learning, what will do is that it will receive this x, it will do the transformation, it will give us the output of x as in linear, in dimension where we can draw a line. So we give all this job of defining the transformation to deep learning. And now deep learning is doing what? Doing everything between linear model and between the x input. That's basically about the deep learning. And I want to tell you that feedforward networks, they are like, how can I say, first the deep learning networks, and they introduce many new things, new concepts. One concept is backpropagation, another concept is activation function. And now we had a problem of learning exclusive OR, and because the first created deep learning networks in 1960s couldn't solve this exclusive OR problem because it wasn't linear, and indeed we cannot draw a line. We cannot draw a line and solve this linear exclusive OR problem. So what we did is that we used deep learning to make this input x transform into such way, into such direction, into such dimension where we can draw a line. And here also we defined special weight and biases for each layer, and we created 2 layers, and then we used one activation function which helped us to boost our model of deep learning and to draw or to make possible to draw a line in that data distribution. So let's cover that XOR problem. So assume. So for guys who don't know about exclusive OR problem, it's a problem where if a function receives 0, 0, it should give 0. If function receives 1, 1, it should also give 0. If function receives 1, 0, it should give 1. If function receives 1, 0, it should give 1. So here, how can we draw a line here? If we draw this kind of line, which means that this is 0, this is 0, this should be 0, and this should be 1. Because this should be 0, but it is 1. So we cannot draw this kind of line. If we draw this kind of line, 1 fits here and 1 goes here also. It's not also correct. If we draw line this way, this should be 1, but it is 0. So we indeed cannot draw a line here. And then we transform this data set, this dimension, if we call it, to the special dimension where you can see this 1, 1 becomes 1 here. 0, 0 remains, but 1 becomes here. Both of them becomes here, which means that we can draw like this line, right? And then our linear model can learn it, right? Because linear models are simple, they are easy to implement, and if we transform the dimension of the model, dimension of the dataset, then we can implement these linear models. And here, this is our model architecture structure, where we receive x and we multiply it to the weight, so we will get the dot product, and then we will add C bias to the resulting matrix, and we will implement this activation function, which is here rectified linear unit, and then we will get the dot product with this vector, and then we add the B bias to the resulting matrix, and in the end we will receive the dimension where we can draw a line, or we will receive simply the result of the problem. So we will solve the problem. So here what we implement with this W transpose, and if this is H, assumes this is H matrix, and then we will plus to B. So this is kind of a linear, right? Linear model. And this H is that H consists of the same as the linear calculation, multiplication and addition, and then we will use this maximum of 0 or the value, and output of this one is input to the second linear layer. So let's go with this solution given in the book. So assume we say that W, the weight of first layer, equal to this matrix, the C bias equal to this matrix as this vector, the W in second layer is equal to this vector, and then we will say the B value is equal to 0. It means that we just skip this, no need. So we give all the possible input values to the x, so 0, 0, 0, 1, 1, 0, 1, 1. And we will get dot product with W. Then we will receive this one. And we will add to this matrix the vector C, and we will get this one. So this is output of one layer, first layer, and then we will give this output resulting matrix to the activation function, ReLU function. ReLU function, what it does is that it will take maximum of the given value or 0. Here, what is the maximum of 0 and 0? It is 0. What is the maximum of 0 and minus 1? 0. So it will be 0. What is maximum of 0 and 1? 1. What is maximum of 0? 0. So these ones will stay the same, Only one small change is that this -1 will become 0. Here you can see it. And then we get this result. And we will give this matrix to the second W vector. So after getting dot product with second vector, W vector, we will receive this output. And this output indeed the correct output. Because in first case it was 0, 0, it should give us what? 0. In second case it was 0, 1, it should give us 1. In third case it should also give us 1, and in fourth case, in fourth one we should receive 0. And indeed it is working. And in such a way, by introducing the activation function, simple activation function, and by introducing another layer, one more layer, we have solved this exclusive OR problem. And this was the end of first winter in artificial intelligence. So let's talk about gradient-based learning. As we talk about gradient descent, that it is iterative and it helps to find the minimum in the function. And using gradient descent based learning in feed-forward networks is pretty the same as in machine learning. So we should define the cost function, we should define the optimization, and we should define the data set and the number of iterations, and etc. Pretty the same. But I should say that they also have backpropagation algorithm which updates the weight of the layers. It's a very cool algorithm, and it is also a backbone of modern deep learning models. So about cost function. Cost function, as you know, it measures the performance, right? And using the right cost function is very crucial. And in some cases, we usually use maximum likelihood for the cost function of the neural networks. And usually, if we use this, if we will use maximum likelihood, we can come up to the mean square error in regression. We can come up to the cross entropy function in the binary classification by using this maximum likelihood. And let's talk about output units. So output units is that if it is classification, binary classifications, output units are usually 0 or 1. If it is a regression problem, the output units are continuous values, and another common output is softmax output if we have discrete values. So here it talks about linear units, which are indeed continuous values, and they give us the vector, and it is continuous, and it is in the Gaussian distribution. What I can say more? I think that's all about that. And sigmoid units are for binary classification. Sigmoid units is, as you know, we just need to find probability of one classification where y is equal to 1, and by finding this probability, we just solve we just get the output of this sigmoid unit of the result of this binary classification. And we have softmax unit. It's for discrete values. It is for classification. Usually we use for classification of discrete values. Discrete values are values which are countable, which are not continuous, and they belong to multi-node distribution. And by using softmax, we will find the probability of the given x belongs to which class, if there is classes. Assume there is classification problem. We have 5 classes, maybe like 5 types of car, types of vehicle. So when we give the image of track, it should give the result as it is car 1%, it is motorbike, it is 1%, it is truck 10%, it is van, it is 99%, something like that. But overall, the sum of probabilities should be 1. It's from our probability rules. So this is softmax, and then let's talk about. So there are also other output types, and you can also design your output type. But basically, these 3 types are common, and they are in practice also they are common. So now let's talk about hidden units. So as you can see, in deep feedforward networks, we have layers, and each layer has a function which has bias and weight. We get this x vector or x matrix. We will multiply it with weight, and we will add the bias, and then we will perform activation function. And this activation function is crucial. As you can see, thanks to activation function, we have solved the problem of exclusive OR. Like, it was like key, right? And indeed, in many modern architectures, these activation functions are also key, and there are plenty different kind of activation functions. And year after year, there are also many different functions are created. So one of the most popular activation function is rectified linear units. So the function is that maximum of 0 or z value. And these rectified linear units are like very popular, as I said before, and they are doing not that much work, but actually they are doing small job but very good job, because as you can see, if that value is positive, it will stay the same, it doesn't change, so that activation function doesn't affect to the output, right? And if it is negative, then in that case it will affect. So here the key of the rectified linear units is that it gets a maximum of 0 or is given that value. And there are many different similar to rectified linear units. We call them leaky ReLU, parametric ReLU, and recently also, not recently, like 3 years or 5 years ago, there was also JLU. It's also similar to ReLU, and there are different other hidden units, and there are also max out units. So it takes a maximum of that J. And yeah, that's about maximum max out unit. And also here sigmoid and hyperbolic tangent units. So here we can say that we will give the output of that layer as a hyperbolic tangent of given z value, and or sigmoid or any other unit. We can also create manually our activation function. Like that, and there are many different hidden units, as I told you, and we will talk about them in practice. And for example, we can see also here another types: soft plus, hard tank, and radial basis function, and etc. And for today, the last topic is architecture design. As you can see, our architecture in exclusive OR, it had only 2 layers. It had 1 activation function, and the number of units was 4. And architecture design is very key, because thanks to the specific architecture design, we can efficiently solve certain problems. And indeed, as I told you before, there is no free lunch in artificial intelligence, so that There is no universal architecture design which can fit for all problem in AI. And this architecture design problem solves what? So we don't know how many layers we should implement, right? Or what is optimal number of layers? What is optimal number of units? What is best activation function? Or what is the best cost function? So in that case, this try and error operation of selecting this architecture design and comparing based on the validation cost, based on the validation error or the test error, we can find out the best architecture design for our problem. And we are saying here that if our model depth, if our model increase in number of layers, it will usually perform better and better. So here we are saying that if our model is long enough, it's better to have the long model, because we can, they are explaining that we can split that, and we can also get the, so we can, if we increase the number of layers, it doesn't have bad effects, as I understood from this graph. And then basically they are saying that as we increase the number of layers or number of units in the architecture, overall accuracy increases and overall the error decreases. That's all about architecture design in short. And as information for computer vision, we have special architecture, as we know, I think CNN, convolutional neural networks, and for language we have for NLP we have another one, and we also have LSTM, and we have recurrent neural networks, which are also next topic, very important topic for deep learning. And basically that's all for today, guys. Thank you very much for your time. In next videos we will talk about backpropagation, but for today that's all. See you in next videos. Bye bye.